Right now, you may be traveling through one of the largest known underdense regions in the nearby universe. Not an empty hole, not a tear in space, and certainly not a black hole. This is something far larger and more subtle. A possible depression in the cosmic distribution of matter, stretching across hundreds of millions of parsecs, with the Milky Way somewhere inside it. Astronomers often call it the KBC void, after Ryan Keenan, Amy Barger, and Lennox Cowie, the researchers whose 2013 study found evidence that the nearby universe contains fewer galaxies and less near-infrared light than more distant regions. Other researchers call related structures the local hole or the local underdensity. But before we go any further, one warning is essential. The existence of some local unevenness is not controversial. The universe is full of dense regions and sparse regions. What remains disputed is whether our local underdensity is truly as enormous and as deep as the most dramatic models suggest. And that distinction matters, because if the strongest version of this idea is correct, our cosmic location could be influencing one of the most important measurements in all of science. When we picture the universe, we often imagine galaxies scattered more or less evenly through space. On the largest mapped scales, that is not what we see. Matter forms a cosmic web, clusters and superclusters connected by long filaments and broad sheets, surrounding vast underdense regions called voids. Voids are not completely empty. They contain dark matter, gas, and isolated galaxies, but they contain much less matter than the cosmic average. Depending on how a void is defined, studies and simulations often find that these low-density regions occupy roughly 60 to 80% of the present-day cosmic volume. Most galaxies and most matter, by contrast, are concentrated in the web's comparatively narrow filaments, walls, and nodes. So living near or inside a void would not make us exceptional in the sense of being alone. A large fraction of space is void-like. The extraordinary claim is the scale. Keenan, Barger, and Cowie examined the luminosity density of galaxies in near-infrared surveys. Near-infrared light is useful because it traces older stellar populations and provides a rough indicator of stellar mass. Their measurements suggested that the luminosity density around us rises with distance before approaching a higher value farther away. Interpreted literally, that pattern can look like a local region hundreds of megaparsecs in radius with substantially less matter than the broader universe. 1 megaparsec is about 3.26 million light-years. A radius of 300 megaparsecs corresponds to nearly 1 billion light-years. Double that, and the full diameter approaches 2 billion light-years. That is where the headline comes from. We may live inside a cosmic hole almost 2 billion light-years across. But a galaxy survey does not weigh the universe directly. It counts and characterizes luminous objects, then uses those galaxies to infer the underlying matter distribution. Survey depth, sky coverage, dust, galaxy evolution, selection effects, and the conversion from redshift to distance can all influence the answer. Different datasets have therefore produced different estimates of the local deficit. Some analyses support a significant underdensity. Others find a shallower structure, a more complicated shape, or no void large enough to produce the most dramatic cosmological effects. This is not a small technical disagreement. It leads directly to the Hubble tension.
The Hubble constant, written as h0, describes the present expansion rate of the universe. It tells us how rapidly the recession velocity of a distant galaxy increases with distance. A value of 70 kilometers per second per megaparsec means that for every additional megaparsec of distance, the expected recession speed rises by about 70 kilometers per second. There are several ways to estimate this number, but two broad approaches have become famous because they do not agree.
The first begins with the early universe.
The European Space Agency's Planck satellite measured tiny temperature variations in the cosmic microwave background, the relic radiation released when the universe became transparent about 380,000 years after the Big Bang. Cosmologists fit those patterns with the standard lambda cold dark matter model, usually abbreviated lambda CDM, and then infer what the expansion rate should be today. The final Planck analysis gave approximately 67.4 kilometers per second per megaparsec, with an uncertainty of about 0.5, assuming the standard model. The second approach builds a distance ladder in the late universe. Astronomers use geometrically calibrated objects to determine the true brightness of Cepheid variable stars. Cepheids then calibrate Type 1a supernovae, whose observed brightness can be used to estimate distances far into the Hubble flow. The SHOES collaboration, led by Adam Rees, reported a value close to 73 kilometers per second per megaparsec. Their 2022 comprehensive analysis gave 73.04, with an uncertainty of about 1.04. A later calibration using additional Cepheid anchors produced a similarly high result.
That is a difference of roughly 8%. In everyday measurement, 8% may not sound catastrophic. In precision cosmology, it is enormous. For the specific Planck and Shoes determinations, the discrepancy has reached around 5 sigma or more, depending on exactly which datasets and assumptions are compared. And the obvious explanations have not made it disappear. Could Cepheids be blended with nearby stars in crowded Hubble images, making them appear too bright and therefore too close? The James Webb Space Telescope tested that possibility with sharper infrared observations. In a 2024 study, Rees and colleagues compared more than 1,000 Cepheids observed with Webb and Hubble. They found no distance-dependent offset large enough to explain the tension and rejected unrecognized Hubble crowding as the cause at more than 8 sigma. That does not prove every part of the distance ladder is perfect. It means one of the most discussed systematic errors appears far too small. So what if the extra recession speed is real, but not entirely global? Imagine a large underdense region surrounded by denser walls, filaments, and clusters. Matter inside the underdensity feels a stronger net gravitational pull toward those denser surroundings than toward the emptier interior. Galaxies develop peculiar velocities, motions in addition to the smooth average expansion of the universe. At the same time, an underdense region evolves differently from a dense one. There is less matter inside it, so gravity produces less deceleration of the local expansion. The void becomes emptier relative to its surroundings, while matter flows toward the walls.
The dark energy does not need to be stronger inside the void. The difference arises mainly because there is less matter available to resist the expansion and less gravity pulling the interior back together. Now, place an observer inside that region. When the observer measures the redshift of nearby galaxies, part of the signal comes from the global expansion, and part may come from local outflow. If those contributions are not fully separated, the locally inferred Hubble constant can be biased upward. The mechanism is physically real. Local density fluctuations do create peculiar velocities and some cosmic variance in H0. The crucial question is magnitude. Can the effect raise a global value near 67 to a local value near 73? Within standard lambda CDM, most studies say no. In 2019, Darcy Kenworthy, Dan Skolnick, and Adam Rees examined 1,295 Type 1a supernovae over a wide range of redshifts. They searched for the distance redshift signature expected from a large local outflow. Their analysis found no evidence for a sharp transition in the Hubble constant across the proposed void boundary, and reported that large underdensities deeper than about 20% were inconsistent with the supernova data at roughly 4 to 5 sigma, depending on the model.
They estimated that ordinary large-scale structure should contribute only about 0.4% cosmic variance to a local Hubble measurement. That is real, but it is nowhere near the full 8% tension. This is why the safest statement is not that the KBC void solves the Hubble tension. It is that a sufficiently large and deep void could, in principle, bias a local measurement, but the void required to erase the entire discrepancy is difficult to reconcile with standard cosmology and with several supernova analyses. The debate has not completely ended. Moritz Hasselbauer, Indranil Banik, Pavel Krupa, and other researchers have argued that galaxy counts support a much larger underdensity, and that its gravitational outflow could account for a substantial part of the local redshift excess. Their models can reproduce several observations, but they often require structure growth stronger than standard lambda CDM predicts, sometimes using modified gravity frameworks such as MOND as a proxy. Those models are scientifically interesting, but they are not the consensus solution. MOND-based cosmology remains controversial, and the inferred void depends strongly on how galaxy counts, velocities, and distances are modeled. Recent baryon acoustic oscillation and velocity studies keep the debate alive, while major reviews still conclude that a conventional local void cannot remove the Hubble tension. In other words, the whole may be real in some form. Its power to rewrite cosmology remains unproven. Our motion through this landscape is also real. In 2014, R. Brent Tully, Helene Courtois, Yehuda Hoffman, and Daniel Pomeray mapped galaxy flows and defined our home supercluster, Laniakea, as a vast gravitational watershed. It extends roughly 500 million light-years and contains on the order of 100,000 large galaxies. Laniakea is not one rigid, gravitationally bound object. It is a flow-defined region within the cosmic web. The cosmic microwave background provides a useful reference frame. Its dipole indicates that the local group moves at about 627 kilometers per second relative to the CMB, or roughly 2.3 million kilometers per hour. This is not the Milky Way being fired out of one spherical hole toward one wall. The local void, the proposed KBC underdensity, the Virgo cluster, the Great Attractor region, and more distant structures all contribute to a complicated three-dimensional velocity field. The map resembles a landscape of basins, ridges, and watersheds, not a single bubble with us at its center. That last point is important. A perfectly spherical giant void centered exactly on the Milky Way would raise a profound version of the old Copernican problem. Why should we occupy such a special location? Observations do not require that exact cartoon. The proposed structures are irregular, and some models place us away from the center. But the more extreme the void must become to solve the Hubble tension, the harder it is to avoid fine-tuning and conflicts with other observations. There is a tempting speculation that a quieter, large-scale environment somehow helped life emerge. Environment does affect galaxy interactions and active galactic nuclei, but there is no evidence that the KBC void caused life on Earth. Habitability depends far more directly on the Sun, Earth's orbit and composition, the local stellar environment, geology, chemistry, and biological evolution. Connecting life to a billion light-year underdensity would be speculation, not established astrophysics. Every cosmological measurement is made from one location, at one time, inside one particular pattern of structure. Cosmologists correct for local motions, average over large volumes, compare independent probes, and test models precisely because our viewpoint is not perfectly representative. And the universe will not always offer observers as much information as it offers us now.
Cosmic expansion is accelerating. At sufficiently large distances, space between galaxies grows so rapidly that newly emitted light from those galaxies will never reach us. This does not mean galaxies are locally breaking the speed limit by flying through space faster than light. General relativity allows the distance between widely separated, unbound regions to increase faster than light because the metric of space itself is evolving. Over tens to hundreds of billions of years, galaxies outside our bound neighborhood will become increasingly redshifted, dim, and inaccessible. Even the famous Milky Way-Andromeda merger is no longer treated as absolutely inevitable. Recent simulations give very different probabilities depending on the measured motions, masses, and satellite galaxies. Whether the two spirals merge or merely interact, the distant cosmic web will fade from the sky of far future astronomers.
Abraham Loeb calculated this long-term loss of extragalactic information in 2002. Lawrence Krauss and Robert Scherer later showed that in a universe permanently dominated by a cosmological constant, future observers could lose nearly every familiar line of evidence for the expanding universe. Distant galaxies would disappear beyond practical observation. The cosmic microwave background would redshift to wavelengths so enormous and temperatures so low that it would become effectively undetectable. The primordial abundance signatures left by Big Bang nucleosynthesis would be altered inside generations of stars. A future civilization could build extraordinary instruments, make flawless measurements of its remaining island of bound galaxies, and still infer a radically incomplete cosmic history.
That does not mean reality is deliberately hiding the truth. It means information is constrained by horizons, cosmic evolution, and the observer's position. And that brings us back to the possible hole around us. The KBC void may turn out to be a deep, enormous underdensity that exposes a weakness in the standard picture of structure formation. It may be a shallower and more irregular feature that slightly affects local measurements, but does not solve the Hubble tension. Or some of the apparent deficit may shrink as surveys improve and models become more complete.
New galaxy maps from projects such as DESI and Euclid, better peculiar velocity measurements, more Webb observations, gravitational wave standard sirens, and independent distance indicators will continue testing these possibilities. For now, the evidence supports a careful conclusion. We do live in an uneven universe. The Milky Way occupies a structured local environment shaped by voids, filaments, clusters, and gravitational flows. There is credible evidence for a local underdensity on very large scales. But the most extreme KBC void remains disputed, and the claim that it fully explains the Hubble tension is not established.
Still, the central idea survives every correction. Where we stand can influence what we measure. The universe does not present itself from nowhere. Every map begins inside the territory. Every telescope looks outward from a moving galaxy embedded in a web of matter. And every number we call universal must first be extracted from the view available at one small point in space and time. Perhaps the most unsettling possibility is not that we live in a cosmic hole. It is that we may never know how many features of the universe remain invisible because we are already inside them.